It is my great honor to introduce the next keynote speaker, Dr. YongXing Zhou. He is the Vice President of Huawei Wireless Radio Access Technology Department and the head of the MIMO and the Spectrum Research Center. He is currently working on 3GPP LTE Plus and 5G technologies. Before he joined Huawei, he also worked in Samsung in various positions in the research and standardization. He has a lot of contributions in these 5G wireless areas. And most notably, he has 100 issued patents. And Dr. YongXing Zhou received a PhD degree from Tsinghua University in China. Let's welcome Dr. YongXing.
Good morning, ladies and gentlemen, professors and experts. Thank you for the coming. Actually, by the end of this week, the 3GPP will finalize its phase 2, the phase 1 standard, and this is expected to be approved in the next month. So we are now really in the 5G, and the 5G new era is here, is open. For me, myself, I'm very lucky. I devote myself to the research of communication, cellular communication, ever since I finished my PhD study in Tsinghua University, which is 16 years ago in 2002. And my talk, actually, I have experienced the part of the 3G standardization and the whole 4G standardization and the 5G standardization ever since the beginning. So I have witnessed the success and the prosperity of the 4G LTE. We have now 7 million base stations around the world. So now we are in the 5G era. So my talk today is bringing 5G into reality. Actually, strictly speaking, we shouldn't talk about the bringing 5G into reality. What I should want to say is bringing the great 5G into reality. For better or worse, 5G is already here. So, but we do expect 5G can provide more. It can be enabler of the full industry digitalization. It can be also our essential foundation of the fourth industrial revolution. So whether the 5G can successfully do its job, fulfill this requirement, we have the unprecedented challenges, which I will talk in my presentation today. But before that, I'd like to shortly review this current 5G industry insight, including the use cases, spectrum, standardization, and Huawei 5G activities. So according to our wireless lab research, we prioritize the several 5G use cases, which you can see here, the video and augmented reality and virtual reality, connected vehicles, smart manufacturing, and fixed wireless network. These are the top 5 use cases we consider according to its 5G relevance and the importance in the business. So the standardization, as I just mentioned, now we are at June, almost June of 2018, and this week will be last working group meeting for 3GPP new radio specification phase 1. And the phase 1 specification will establish the 5G foundation and mostly targeted for the enhanced mobile broadband. And the resisting phase 2 will focus on the fulfill of the ITU IMT 2020 requirement, basically the other 2 corners we see in the ITU 3 triangle diagrams. So on the other hand, the LTE is still ongoing, and it could be part of the 5G. Actually, there will be 2 proposals to 5G ITU, the 5G new radio and the LTE evolution. So regarding the spectrum, the 5G new band, including the C-band, as well as the millimeter wave. The millimeter wave, the C-band is very well already harmonized across the world. Basically, we have roughly 200 megahertz. And the millimeter wave, including the group 30 gigahertz and the group 40 gigahertz, this will be defined and allocated in the coming World Radio Communication Conference 19 next year. And then after that, the commercialization will be ongoing. So far we see this C-band 3.5G and group 40, group 30 will be a very good potential global harmonized band. That's the basic spectrum we see for 5G. We see that compared to the 4G LTE, the spectrum frequency is a little higher, shifted to the higher position. But this should be the first wave of 5G spectrum. So I then would like to update some Huawei activities in the 5G. So Huawei has a collaboration with more than 30 leading operators across the world, including this China Mobile, Docomo, Vodafone, and so on. We have also leading the many 10 plus 3GPP 5G pre-commercial networks. So in the IMT 2020 test field trial, just on 2017 last year, Huawei finished the first phase and the second phase test, and all of the testing results are way ahead. We can see the new core and the radio access network, CPE and the chipset. Huawei provided this full, most complete end-to-end system. And we conducted the full spectrum test, including the 3.5G and 4.9 gigahertz band, also 28 gigahertz and 39 gigahertz millimeter wave band. With the C-band test, we found the cell throughput of peak rate could be as high as 28 gigahertz and the lowest latency 0.33 millisecond. It can provide also the 1 billion connections per megahertz per hour and per cell. So we also conducted the most comprehensive interoperability test with the chipset and instrument vendors with the live use cases of 4K video and connected cars in the real live network. We show there. The millimeter wave and C-band dual connectivity field trial was also done last year. We did this with LG U+, and we found that with the dual connectivity, you can achieve more than 20 gigabps peak throughput and more than 2 gigabps per user throughput. And we launched this first 5G millimeter wave fixed wireless service in Vancouver. And within in the 650 meters range, the user throughput could be as high as 2 gigabps. This is in the real network we tested this. And then the first 5G ultra reliability and low latency field trial was also conducted and jointly with Docomo in Yokohama in Japan, November 2017. In the band of 4.5 gigahertz with the 20 megahertz bandwidth, we can provide the more than 5.9 reliability and less than 1 millisecond latencies. So we also conducted the 5G new radio-based tele-operated driving trial with China Mobile and Shanghai Automotive Industry Corporation last year. We actually can control from 50 kilometers away a car and with less than 10 millisecond latency, and can supply 50 megabps, which can support 4 ways of the high definition video. So this kind of services actually can be used in the application scenario of the shuttle bus or mine truck, and so on. So I'd just briefly introduce this industry insight situations of 5G current status. Then I'd like to address the new challenges for 5G and beyond, how to fulfill the requirement, how to fulfill the full digital industry full industry digitalization and fourth industrial revolution. We have the several aspects in terms of the architecture challenge and capacity and coverage. This is the typical mobile broadband service problems, and we will address what's the new problem for ultra-low reliability and massive connections. So this is architecture specified in 3GPP. Last year, end of the last year, the non-standalone architecture was specified, and this month the standalone architecture was specified. So basically the non-standalone architecture using the LTE and EPC as the anchor. This is for the very early and quick deployment introduction of the 5G. Actually, it's mostly the user plane air interface. But for the standalone architecture, it's a full 5G supporting the features. For example, the network slicing using the new core will be supported very well in the standalone architecture. So that's the status for the architecture so far. In terms of this base station, 4G, we have this compact CU, DU in one base station. But now in 5G, there's a split between the PDCP layers and the lower layers. This is for more flexible and low-cost considerations. That was decided in last year, and the option 2 is finally agreed. We can basically split in many places, but actually this is the best trade-off and decisions. So regarding this architecture, I see the problem, I see the benefit, I see the advantages of this. Basically, we want to support the slicing. We want to support various of the services. We call this service-oriented radio and network. In the network side, you can orchestrate, virtualize the resources and push the core to the edge if necessary, if the low latency is required. On the other hand, we can also find in the air interface part, we have a lot of configurabilities and a lot of flexibilities, which is more than LTE, to support all of these use cases, scenarios. But this biggest problem for that is we done the part of the configurability to make this flexible, to make this slicing enabled. However, the question is, we see this architecture. We don't, but so far we didn't support very well the service is aware. So that's the problem we should solve for the next stage. Also the sharing mechanism, because all of these services, these virtual applications are sharing basically the same resource. How to make these services shared or multiplexed very efficiently, that's a very challenging question. Of course, we can do that if we have unlimited bandwidth and unlimited resource. Everything is possible, but the resource is limited. The efficiency is a very good question and the key challenging for this. That's from my point of view. We see this sharing as in this page, in this previous page. We see this sharing happens. Actually, it could be done in different layers. The lower the layer it happens, the more complex and more challenging for this handling. We need more and more intelligent, smart way to handle this multiplexing or sharing things. But on the other hand, the lower the awareness and the layer it is, we can foresee the more values of this sharing, the more efficient we can see. So this is the architecture challenge I have addressed. It is just an efficiency issue, how to support slicing, network slicing, radio slicing most efficiently. And then let's talk about this MBB issue. We have the capacity and the coverage. This is basically the two things we have to address all the time, all of the releases, all of the generations. So how to pursue the good spectrum efficiency, how to achieve a better coverage. So regarding this spectrum efficiency, we found a new consideration is needed because at this moment we have seen this quality of service is very crucial. The capacity actually or spectral efficiency highly depends on the quality of service. And we see the trade-off we can find in the left, on the right upper figure. The more of the cell resource utilization we have, for example, we have a resource utilization of a spectrum up to 80%. That's good because you use more of your resource and your spectrum. But on the other hand, we see this user experience is dropping down. So that's a basic trade-off between this user experience and spectral efficiency. So basically in the real network nowadays, for example, in LTE network, most of the network is working at very low load, very low resource utilization. What's the reason? Because if you have to increase the ratio of the resource utilization, if you want to have a better spectrum efficiency, then it means the quality of the service, the user experience will be bad. So basically we are trying to discuss what's the proper metric to measure the spectrum efficiency, how to measure the capacity more properly. So we are going from the full buffer spectral efficiency measurement. We know that very long time ago we do this and it could be useful. But however, in this evaluation, nobody cares about how the user feels. Some users may be very bad. And then we turn to the user experience metric, which is finite buffer traffic, and we check how the user feels. The user feels it's good, or it's quick, or it's fast, or it's slow. But this is the user experience. Now, if we combine this together, we just check how about to align the user experience of two different technologies. And at this moment, we check how much throughput, the cell throughput, spectral efficiency, the different technology can approve. This is very interesting. We conducted this massive MIMO evaluation with these two different metrics. First of all, we check this full buffer metric in the band of the 1.8 gigahertz. This is the FDD band of 4G LTE nowadays. We check this two antennas and base station, compare this with the 32 antennas and the base station. The result we find is there's 7 times of spectral efficiency enhancement over the 2T, the 2 antenna, because this is the 32 over 2. But if we look at this, how this 7 times of the efficiency improvement comes from, we realize most of the gain is from the multi-user MIMO, which means you support many users in the same frequency, time, resource. But unfortunately, this multi-user MIMO pairing is very difficult. It's sensitive to the traffic. It is also sensitive to the user distributions. So this is not very reliable. If we just drop all of the multi-user MIMO, SD, MA gains, we realize this is only 60% of the robust SU MIMO gain. But however, if we change to a burst traffic, and we using the new metric we see, we still compare this massive MIMO performance with 2 antenna performance. We see there's as large as 20 times of the gains. Within this 20 times of gain of this is 32 antenna over 2 antennas, we find Even there's only SU MIMO, it's just a single user MIMO in the system, which basically means the base station transmits to one user. This is just a link, one link from a base station to the users. It can provide 11 times of spectrum efficiency gain. So how this is come from? It is because if we compare the massive MIMO and two antenna systems, besides the good signal-to-noise ratio, SNR, and the more layers can be multiplexed, we see in the two antenna system, it has to work in a very low resource utilization condition. But for the massive MIMO, because of the good technologies and good advanced signal processing, the more utilization of the spectrum it can be allowed. It is just 20 megahertz bandwidth. Actually, in the two antenna systems, we just use 20% of the resource utilization. But in the massive MIMO, we can use as high as 60%, just because we align this user experience. So this basically means if the user have no notice of the user performance, no drop of the experience, 20 times of the more throughput can be provided in massive MIMO system. This is very interesting, and we need to reconsider the balance of the user experience and the spectrum efficiency. Now we see for massive MIMO, we can fully utilize these potentials, not only because of antenna processing, but also we utilize more resources. That's the thing. Then we go to the C-band TDD Massive MIMO. Many people will argue, for TDD, you can use the sounding and UE, the user terminals, sending the sounding signals, and the base station can marry and using reciprocity to achieve the downlink channel. It seems good, but still there are a lot of questions and a lot of problems. So one of the problems for sounding, it is the coverage. We found the problem of the 3.5G coverage because the coverage, the sounding is sent by the user terminal, it's power limited. If the sounding quality is very bad due to your power limitation, so the channel reciprocity, the downlink channel state information cannot be as accurate as we expected. Another case is, so far in our user terminals, our UE handphones, mostly is asymmetric. We have more receiver antennas than our transmitter antennas. This is because the power amplifier is more expensive. So basically, if we use this one transmitter antenna and 4 receiver antenna user terminals, so we can only acquire not a part of the channel state information. So there are still a big gap between the ideal case and what we can do so far. So even TDD, there are a lot of challenges for the spectrum efficiency. For the 4 antenna system, because previously we talked about this massive MIMO, 32, 64 antennas. But how about these basic 4 antennas and 8 antennas for the lower frequencies, which could be very important in the refarming phase of 5G. Of course, the first phase, the first wave of 5G is in the C-band and, as I said, the mmWave. But this could be the second phase for lower frequencies with the 4 antennas, 8 antennas. Basically, due to this good air interface of 5G, the MIMO enhancement and this air interface latency reductions and the reference optimizations, pilot optimizations, we can achieve as big as 3 times spectrum efficiency. So that's pretty much for the capacity. We see there are big rooms to enhance. We still need to work on that. The spectrum efficiency is, we are trying to work on that, reduce the bit the cost per bit. And then we realized that the 5G, the spectrum is a little higher in the frequency than LTE 4G. We checked this C-band and 1.8 gigahertz trial. We found in the trial there are a lot of gap between these 2 spectrums. It's 10 to 8 times of the gap. So how to address that? We find we can utilize this uplink of this lower band to complement this higher band. In the C band, it's TDD, both downlink and uplink can use the same band. But we can also complement this 3.5G of uplink with lower band. By doing that, it is defined in 3GPP, the uplink spectrum uplink sharing, and uplink and the downlink decoupling. Because of this new band introduction, and we find basically in the real trial with BT, Huawei and BTE, we found this in London, up to 11 dB of coverage is enhanced. But this is due to the utilization of the lower band in uplink. The problem that how to deal with this C-band only case. It's very challenging if you have to rely on the pure, you just in the 3.5 higher frequency band, if you want to compensate this 11 dB coverage hole, this is very, very challenging. We still need to work on this. And if we go to this mmWave fixed wireless connection, we call this wireless to the home, to anything. This is more challenging. We find this, there's non-line of sight, line of sight scenarios. There are different coverages. In the worst case, this is the simulation. It could be just 74 meters of the coverage. That's very bad, and it means a lot of cost and deployment difficulties. So the problem, in the standard, there are several technologies trying to address this issue. So one technology is this beam-based access, which means not only these data channels, but also these common channels and pillars. They can all be beamformed and swept, like broadcasting channels and synchronization channels. This is one technology. And the waveform, in the uplink, it could be switched between the DFT SFDM waveform and OFDM. It can also support the lower PAPR modulations, the half-pi BPSK. It can also support this spectrum shaping without a spectrum extension, which of course this is an implementation domain for further PAPR reduction. But basically there are some work already done in the waveform and the modulations to reduce the PAPR. That's for the good coverage. In the uplink demodulation or pilot channel, the new computer-generated sequences were supported. We can find these figures, no matter the cubic or PAPR, is around 1 to 2 dB better than LTE with the same cross correlations between the different cells, so between the different sequence groups. So this is good because this reference signal or pilot can provide 1 to 2 dB over LTE. That's the coverage effort we have already done in 5G new radio. And in Release 16, we are considering the integrated access backhaul for further coverage enhancement for mmWave. Let's see how much we can improve if we go back to check this mmWave coverage after Release 16 and maybe 17. And then let's go to this from mobile broadband to full digital society, basically the two other corners in the ITU triangles. Firstly, let's talk about this ultra-reliable low latency. So there are several items, there are several topics related to that. The common, ultra-reliable, low latency communication study and this industrial IoT study and the cellular V2X. We see this from LTE to 14, 15, and until 5G. These KPIs, the key indexes, performance indexes, are becoming more and more beautiful. So it can support more and more services and more use cases. And if we check this, both figures show the same case. We see that more cases and more beautiful KPI to support it. In Release 16, there are some things we are ongoing, like the introduction of several features, integrate this 5G connectivity with the industry Ethernet, and probably integrate of the wireless time-sensitive network on in the 5G. So what's the problem behind? We see behind these beautiful KPIs, the problem is when the time slot is getting smaller and smaller, the overhead, which means the pilot and the control, usually our system design, is getting bigger and bigger. So this ratio of the overhead is becoming larger. And at the same time, the new information theory with the finite code block length tells us these KPIs, these key performance indexes, the capacity, this availability, and this reliability, these several metrics, these KPIs, they are not independent. They are bounded. There should be a best trade-off, a boundary exist. We just did a very simple check, and you can find this curve. The yellow curve means this information theory and the mutual information with finite, of course, with finite code block length. It's not a pure Shannon capacity curve. And we check this is the red one is the 5G new radio control channel performance. We're just trying to transmit 10 byte data with 10 byte control information. We found and we observed 8 dB link performance gap exists. So there should be this should be a very big gap if we turn into a system level simulation. This could be several times of the spectral efficiency differences. So this is 8 dB, and how to solve it, I don't have the specific ideas, but we can try to work on that to make this gap disappear. This is a problem we need. The efficiencies of behind these beautiful KPIs is ignored so far. And on the ultra reliabilities, we have to say this, go back to these use cases. We see cloud-based augmented reality and virtual reality. This is very important, and we also see this cloud-based rendering will provide the best trade-off between the performance and cost. So if we only provide this entry-level experience, the requirement for the network is capacity is 128 megabps. Data rate is fine. But if we want ultra retina experience, then this 3.2 gigabps or 5 millisecond latency, this is required. For this, we are in our mixed reality to make this come into true. There are many challenges, many fields we should take a look, including these new display materials and the new evolution of processing, the neuromorphic computing, for example, and the deep perceptions. Of course, we need ultra-fast networking and the AI, artificial intelligence technologies embedded for this full system. So that's for the ultra-reliability, low-latency communications. For the low-power wide area IoT, this represents 70% of the cellular IoT connections. We already have this narrowband IoT and MMTC specified in LTE. We need to find the new use cases. For example, this smart retailing and logistics, which basically means the even cheaper cost for this new IoT terminal, and provide wide coverage and even lower power consumptions. For example, this back scattering energy harvesting could be a potential to achieve this. That's what I want. That's the massive connections. Basically, we already have this in MBIoT and MTC. We need to find more use cases to address this, and new technology to address these new use cases for low power wide area applications. And we have these challenges now, not only the spectrum. We have the spectrum how to support a full range of spectrum from very low spectrum, below 3 GHz, and middle spectrum, and until very high mmWave spectrum. So these are the challenges we have to tackle with different spectrum. This is a much wider spectrum we have to deal with than LTE. And then we have the many services and even many industries there. And then we need to map all of these services, industries, applications with this spectrum. So we can see there will be much difficult and many challenges. I'm not an expert on different vertical industries. We only abstract this requirement from the industries to some very simple key performance indexes, like, for example, ultra-low reliability, low latency, which means 32 bytes transmit in 1 millisecond with the reliability of 509. That's it. But this can solve all of the requirements from the industry. We don't know. So what type of the research is needed? Spectrum, size, architecture. This is the normal, typical research areas we should focus for the from 2G, 3G, and 4G. But now we have the verticals. We have the different industries. We want all of the industry digitalized. And so we have to know their need and what's the map of these industries, how to translate into this typical physical layer and cellular communication area. We need some translations between the different industries. So we also need to ensure that we know how to ensure this full potential of the 5G is not only possible, only one company or one industry like our telecom can fulfill this. It needs a full collaboration ecosystem to achieve this. So with that, I finish today my presentation. Thank you.
Thank you so much for the talk. So the first question is that, do you consider device-to-device communications a key enabling technology? If so, how the ISP will react to it?
This is a very good question. Actually, I didn't focus too much about device-to-device communication. But to me, my own personal understanding is this has become essentially important in the connected cars applications. The cellular V2X, I introduced a little bit in this, but I do think this is very important in these applications. In D2D, it is supported already in LTE, but this is purposed mostly for discovery and public safety for this type of application. But in 5G, I think it is very important. We have a more powerful use case application scenario, which is the connected cars, vehicles. This is could be more play a more important role in this. Technology itself is there, it's good. I think whether it's popular or become whether it can be applied widely. So we have the application scenarios now. I fully believe this could be a very important technology component in 5G. Thank you.
Thanks. So the next question is that 5G will serve traffic with different QoS requirements.
Yes.
What about the ways to provide the network with the knowledge about exact requirements for each particular flow? How will it be done?
Okay, this is a tough question. Actually, this is a very tough question because our communication is done in this way. It's divided into layers, and there are some information change between layers. But if we want this full awareness of the services, It could be a very basic architecture change. I think it's very, very difficult. But on the other hand, if the service is not aware, even know at least for the base stations, how can we see these efficiencies can be optimized? It's very miserable. I don't see we can do that everything transparently, or even the deep the perceptions on that. This is not very good. But I think it's a very tough and good question. We should work on that contiguously, step by step. More and more information to be awareness. That's for sure is a question. It's a trend. But we're just not sure how much, how transparently this information can be get by the human being.
Thank you so much for the talk.
Okay. Thank you.